I will be talking about a parametric programming-based approach to approximate selective inference for selection by the adaptive lasso, the adaptive elastic net, and the group lasso. And this is joint work with my PhD supervisor, Gerda Klaaskens. So I will first introduce the topic to you, then we'll get into the method for computing p-values and confidence intervals post-selection. I will then show some simulation results, a data application, and conclude. So my research is in post-selection inference, or conducting hypothesis tests after model selection. So when we conduct model selection, we mine the data for strong associations, which we then include in a model. And typically, we only want to assess the significance of the associations that we included in the model and ignore the other ones. And when we do that, we have to take into account that model selection step. And I will now explain why. So classical inference actually assumes that the hypotheses were fixed before seeing our data. This is because it controls a nominal type 1 error probability at a level alpha. So under the null hypothesis, the probability to reject the null hypothesis should be smaller than or equal to alpha. Instead, in post-selection inference, we adaptively choose based on our data the hypotheses that we want to test. And so we must control the type 1 error given that this hypothesis was selected for testing. And this prevents us from considering the fact that a parameter was selected as extra evidence against the null hypothesis, which would be using the same information twice and is also called double dipping or data snooping. And so essentially our goal in post-selection inference is to obtain p-values which satisfy the property that they are uniformly distributed between 0 and 1 under the null hypothesis, given the model selection. And classical inference does not satisfy this property, and I will later illustrate this in some simulations. So there are different ways of dealing with post-selection inference. Of course, the most common approach, though not always used, is data splitting. So where you split your data into two subsets, use one for model selection and the other for inference. Of course, the issue is obvious here. You have less information available to you, both during model selection, leading to poor model selection, and during inference, leading to less powerful inference. And then we have some approaches which can be categorized under the name simultaneous inference, where intervals are proposed which are valid no matter the model selection method post-selection. An example of these are the so-called POSI intervals by Berg et al. And so these are not specialized to particular model selection methods and are conservative. In selective inference, SI, however, we condition our hypothesis tests on the subspace of the data that would lead to the same model as our observed data did. And this leads to more powerful inference because you really exhaust all the information available to you in your sample by conditioning on a specific selection event. And a lot of work has been done in selective inference for selection methods where that subspace of the data, which leads to the same model as your observed data did, can be characterized as a polyhedron, so as linear inequality constraints on your response vector. An example of this is the lasso. And in our work, we try to contribute by proposing an algorithm for selective inference after selection methods, which do not necessarily have to be describable as a polyhedron. And we apply this to the adaptive lasso, the adaptive elastic net, and the group lasso. Our approach is approximate, but simulations will suggest that it controls the type 1 error, unlike naive classical inference, which I will call naive inference from now on, and it looks more powerful than than data splitting and the POSI intervals. So we assume a response vector y, which is normally distributed with a certain mean mu, which will be modeled as a linear function of p variables. And we will select variables with methods of regularized regression. So of course, the Lasso adds the L1 penalty to the objective function with a certain regularization parameter lambda, should be equal, bigger than or equal to 0. And this leads to some coefficients being set to 0, and hence to model selection. The adaptive Lasso adds to that a vector W of coefficient-specific weights. These are typically based on the inverse of some first estimate of beta. The idea is that this leads to consistency in the model selection. The adaptive elastic net adds to that the L2 penalty to the second power, which makes the loss function more convex and is useful in cases of multicollinearity between covariates. And then the group Lasso instead uses the L2 norm for groups of coefficients. So this allows us to specify groups of coefficients which should be included in the model simultaneously or not. An example of this are a bunch of categorical covariates with different levels. So Pj here denotes the number of levels within a group. If this is 1, then Pj drops and the L2 norm becomes the absolute value again. So then the standard group Lasso penalties, the standard Lasso penalty is retrieved. And so all these objective functions leads to a set of selected coefficients that we call the active sets, hence the notation A of y. So our selected model is a linear model using the columns that we selected, and we want to conduct inference for the best approximating parameter value in the selected linear model. So this is our target of inference, and this means that we allow our mean to be misspecified. We use this notation eta j simply such that eta j transpose y equals the OLS estimator in the selected model for the j selected coefficient. So we restrict the columns of x to the active set, and ej is simply a basis vector of the length of the active set with 1 in the jth row. And so we simply want to test the hypothesis whether the partial regression coefficient of the j selected coefficient in the selected model is 0 or not, or at least its best approximating parameter value. To test that, we have to consider the sampling distribution of eta j transposed y, conditioned on this conditioning event here. So we condition on the active set based on a random response y being the same as the active set that we have with our observed response. And second, we also condition on the projection of y onto the orthogonal complement of eta j. So this is done to get rid of nuisance parameters. And then the probability integral transform can be used to obtain p-values which are uniformly distributed under the null. So big F here denotes the cumulative distribution function of the truncated normal distribution with mean eta j transpose mu, variance eta j transposed sigma eta j, and truncated to z. And in order to get a p-value which is valid given the selection, we simply fit in 0 for the mean to test the hypothesis that I mentioned before. And we evaluated in the observed test statistic, take twice the minimum for a two-sided test. And all of this is actually the same as in Taylor and Tipshirani and Lee et al., except that there, for the Lasso, they find that if they additionally condition on the signs of the selected coefficients, so this is what sy equals sy observed denotes here, that you can actually describe this conditioning event as a polyhedron. So this is just an illustration here. So if you fix the design matrix X and you fix the regularization parameter lambda, then Y can be divided into these different subspaces where every combination of selected coefficients and their signs can be expressed as linear inequality constraints on Y. And so based on this linear characterization of the selection event, Taylor and Cipriani and Lee et al., they derive these formulas to compute the truncation region Z in an exact way. Now, this has to do with the optimality, the KKT conditions of the Lasso, which consist of linear equalities and inequalities. That is not the case for the adaptive lasso or elastic net and the group lasso. Therefore, we cannot describe these selection events as polyhedrons. And so we must find some different way to compute the truncation region Z. In this paper by Liu et al., they actually propose to parameterize the response vector Y by a scalar parameter C, by decomposing Y into its projection, its projection onto the orthogonal complement of eta j, and its projection onto eta j, and then substituting the test statistic itself, eta j transpose Y, by Z. And so now the truncation region Z, big Z, can be computed by identifying for a grid of Z values for which active sets based on a parametrized response vector. This active set is the same as the active set that we observed based on our observed response vector. And so the entire problem becomes reframed in terms of the truncated sampling distribution of this random variable Z. Again, for the Lasso, this is easier than for the other methods of regularized regression that I mentioned, because again, the Lasso is a quadratic program. And so in Dewey and Sakushi, they use the fact that for a quadratic program, if they parameterize the objective function by a scalar parameter, that the solution path of this objective function is a piecewise linear function of the scalar parameter. You can see this here on figure A. And so in a method called parametric programming, they are able to derive the step size that they have to multiply Z with in order to get to the next transition point where the active set changes again. On figures B, C, and D here, I plotted the solution paths of the adaptive lasso or elastic net and the group lasso, and you can see that this piecewise linearity is no longer the case. And so we must again find some other way to compute the truncation region. And so we instead suggest an approach called a sort of approximate parametric programming, where actually a grid search is conducted for a Z between -20 sigma and 20 sigma, where sigma is the standard deviation of the sampling distribution of the test statistic. And this should be large enough since we know this to be normally distributed. And we do this with a certain step size epsilon. The algorithm is summarized here, but I will maybe show some simulation results. So all the simulation results that I will show are based on 1,000 replications, so 1,000 data sets. So in this case, I generated N is 100 responses, Y, with a mean mu, which was modeled as a function of P is 10 variables, where 6 truly zero coefficients. I used the group lasso to select coefficients. And on this plot here, I am plotting the p-values for the test whether a truly zero coefficient equals 0. We are thus under the null hypothesis, and we need these p-values to follow a uniform distribution in order to have control over the type 1 error. On the left part of the plot, both on the histogram and the uniform QQ plot, you can see that this is the case for the p-values which were obtained from our selective inference algorithm, but not for the naive p-values on the right. These are smaller than what one would expect under the null hypothesis, under the uniform distribution. So this means that we reject too often, and we have too many false positives, too many type 1 errors. Here I plotted the length of 1,000 confidence intervals obtained from 4 different methods on a box plot. So from left to right, selective inference, naive inference, data splitting, where the split to the train to test ratio was 50-50%, and the POSI intervals. So in general, the narrower confidence interval, the higher the power. We can see that the naive intervals are the narrowest. And this, of course, makes sense due to the loss of type 1 error rate control. This is not really comparable and should not be used. And then the intervals obtained from selective inference are in most cases shorter than the ones obtained from data splitting and POSI intervals. However, you do see many outlying confidence interval lengths. This has to do with the fact that this is actually a common issue in SI, and has to do with the fact that it is based on a truncated distribution. And if the truncation limits are close to each other, then you end up with a small probability in the denominator, and then these lengths are longer. But in most cases, they are shorter. Then here I plotted again the false positive rate or the type 1 error rates for 3 different combinations of sample size and p for the group lasso and the adaptive lasso. And the lines just connect the different values for easier comparison. So again, you can see that with classical inference, the type 1 error rates, the control over the type 1 error rates is lost. Here I plotted for 3 different sample sizes, the true positive rate for truly non-zero coefficients obtained from data splitting, naive inference, POSI intervals, and selective inference. The highest true positive rate is obtained with naive inference, but again should not be used due to the false positive rate amount. And then selective inference is more powerful than POSI intervals in the first 2 settings, and in all 3 settings, then it's more powerful than data splitting. And then I have a plot of the coverage rate of 95% confidence intervals, which is higher than the pre-specified level for POSI with POSI intervals, which is higher than the coverage rate of where selective inference leads to a coverage rate higher than the coverage rate obtained with data splitting when the sample size is small compared to the size of P. So in the first and the last setting. So for a data application, we applied this to a data set compiled from the National Health and Nutrition Examination Survey, the NHANES. This is a survey conducted with USA residents, which gathers information about the health status and some nutritional information, demographical variables. And we compiled a data set from this, from the last available rounds between 2017 and 2020 pre-COVID, of size N is 5,985, P is 50. The covariates included in this data set can be both continuous, like age, or categorical, grouped or not, or ungrouped covariates, like educational level. And so we wanted to build a model for body mass index, and we used the group lasso, which can handle selection, variable selection in this type of setting. We selected 15 variables to estimate body mass index with, and we then wanted to assess the significancy of the effects that were included in the model. And so we therefore computed confidence intervals obtained from selective inference, data splitting, again based on a 50-50% split, and naive inference. And on this plot, I would like to draw your attention to 2 effects So for instance, for the variable smoke on the right, you can see that the confidence interval obtained from classical inference, from naive inference, excludes 0. So you would conclude on a 95% significance level that smoking has a significant negative effect on BMI, whereas when you take into account the selection, this interval actually includes 0. And then in the middle, for the variable diabetes, the category borderline, from this, for this effect, you would conclude with selective. You conclude with selective inference that there is something significant going on here. So people with borderline diabetes have a positive association with BMI, and this, as opposed to no diabetes. And this effect is not detected when you data split. Of course, this is an application, so we are not sure of the true parameter value, but based on the simulation results, one might suspect that data splitting might be missing something significant here. So to conclude, we proposed a method of selective inference, which can be used after selection events which do not have to be expressible as polyhedral constraints on the data space. And we apply this to adaptive lasso, adaptive elastic net, and the group lasso. To conclude, this approach is approximate, but it is rather quick, and it is more powerful than data splitting, because you really exhaust all the information available in your sample instead of having to condition on the entire selection set. You condition on the specific selection event. And use all of your data for inference. There is an issue, however, with some outlying confidence interval lengths. Again, this is in the area of SI, a common issue. And a promising avenue for dealing with this has been to add a randomization term to the objective function. This is what I had to say for my presentation. Thank you.
Thank you very much, Sarah, for the very nice talk. And are there any questions from the audience? Please feel free to unmute yourself to ask the questions, or alternatively, you can also type your questions in the chat. Okay, so maybe I can ask a quick question. So Sarah, when you comparing against the data splitting method, did you consider the single data splitting method? I just wonder, like, if you have considered like a more like multiple data splitting to split the data multiple times and then like somehow combine the test statistics. This probably might yield like a more powerful test. Have you considered
splitting multiple times? Are you talking about multi-splitting, or did you mean different train to test ratios?
I mean, just to split the data multiple times into different like testing and selection folds, and then to somehow to combine these test statistics.
Right.
So,
yeah, I think this is something that has been done. It's called multi-splitting. Which is also an interesting approach. Yeah, I'm not an expert on multi-splitting, but I didn't use it in this setting because the idea was really to use a selective inference approach where you, this is also called data carving, where you carve the data by using all of your information for inference. But there is also something like that, and it's called multi-splitting.
No problem. Thank you. And I think there's another question from the audience. So Henrik, do you want to?
Yes. So I wonder, do you have like, if I would like to use your method, do you have like an R package or an implementation that a user can use or get access to?
I have no R package. The code is available upon request. So I can definitely share code for this, but it's not publicly available yet. Yeah.
Okay, thanks.
Thank you for the question.